Silicon carbide membrane tube, a cross-flow filtration element built from a porous silicon carbide support body with a precision separation layer coated on either the outer or inner surface. You are looking at three standard configurations. The first is a single-channel tube with the membrane on the outside. The white outer coating is the separation layer, and the dark porous bore is the support structure. The second is a single-channel tube with the membrane on the inside. Look into the bore and you see the smooth-coated inner wall that does the actual filtering. The third is a 19-channel tube, 19 parallel bores drilled through a single silicon carbide body, each bore coated with an inner membrane. That multi-channel geometry packs roughly 10 times the filtration area of a single-channel tube into the same module length. What separates a silicon carbide membrane tube from a polymer filter cartridge in aggressive industrial service? Start with chemical range. This membrane operates across the full pH spectrum from 0 to 14, handling concentrated acids and strong alkalis in the same system. Pore size is controlled between 0.02 and 0.1 micrometers, placing it in the microfiltration and ultrafiltration range for removing suspended solids, colloids, bacteria, and emulsified oil. After chemical cleaning, CIP with strong oxidants, caustic soda, or mineral acid, flux recovery exceeds 95%, cycle after cycle, year after year. That recovery rate keeps operating costs predictable because the membrane does not lose capacity the way polymer membranes do after aggressive cleaning. Service life extends beyond 5 years in documented installations, compared to 1 to 3 years for polymer alternatives in comparable duty. And thermal stability allows hot CIP at temperatures above 65 degrees Celsius, a cleaning intensity that would destroy most polymer membranes on contact. Each configuration directs the feed and permeate flow differently. The outer membrane single-channel tube is designed for submerged filtration. The feed contacts the coated outer surface, and clean permeate collects inside the bore. The inner membrane single-channel tube runs crossflow through the bore. The feed flows along the coated inner wall at high velocity, and permeate exits through the porous support to the shell side. The 19-channel tube scales that crossflow geometry. 19 parallel bores share one silicon carbide body, multiplying the active membrane area per tube by roughly 10 times. Industrial-scale brine and wastewater systems typically specify the multi-channel configuration to maximize throughput per module. Inside a chlor-alkali plant, saturated sodium chloride brine, roughly 310 grams per liter, must be purified before it enters the electrolysis cell. Suspended solids, calcium, magnesium, and sulfate ions in the raw brine would foul and damage the ion exchange membrane inside the cell, degrading electrolysis efficiency and shortening the membrane life that represents one of the largest operating costs in the plant. A silicon carbide membrane filtration stage upstream of the cell removes those contaminants down to the submicron level. The 0.02 to 0.1 micrometer pore structure captures particles that would pass through conventional sand filters or cartridge pre-filters. And the operating environment is exactly where silicon carbide outperforms every alternative. The brine itself is near saturated salt. The CIP cycle alternates between hydrochloric acid and sodium hydroxide to dissolve scale and organic fouling, and the system runs continuously because any unplanned shutdown in a chlor-alkali plant interrupts caustic soda and chlorine supply to downstream chemical production. A polymer membrane in this position would degrade within months under the combined assault of extreme salinity, acid-alkali CIP cycling, and high-temperature cleaning. SiC handles all three: pH 0 to 14, flux recovery above 95% after every CIP, service life beyond 5 years, and the multi-channel 19-bore configuration delivers the throughput that a full-scale chlor-alkali brine loop demands.